Hey everyone! Ever wonder how a machine learning model can look at a bunch of cat photos and then spot a cat in a totally new picture? It's like magic, right? But behind that magic is some seriously cool math. Today, we're unpacking a concept called function spaces, the mathematical playground where models learn to transform inputs into answers. Let's dive in. Imagine functions as tools. A function is just a rule that takes something in and gives something out, like a recipe. But when we're dealing with machine learning, we're not just using one tool. We're juggling hundreds of functions, each layer in a neural network acting like a different tool in a workshop. The question is, how do these tools work together to solve a problem? This is where function spaces come in. Think of a function space as a library of all possible functions a model could use. But not just any library, this one has rules. For example, if you're building a model to recognize cats, the library might include functions that detect edges, shapes, or textures. The model chooses which functions to use based on the data it sees. But here's the twist, these function spaces need to be well behaved. If the library is too chaotic, like a junk drawer with every tool imaginable, the model might get confused. Mathematicians have developed tools to keep things organized. One of them is covering numbers, which measure how dense a function space is. Imagine trying to cover a table with sticky notes. The fewer notes you need, the simpler the space. This helps us understand how complex a model's library is, and how likely it is to overfit or underfit. Then there's Rademacher complexity, which acts like a flexibility score for these function spaces. It asks, can the model fit random noise as well as real data? If it can, it's probably overfitting. By bounding this complexity, we can predict how well a model will generalize to new examples. It's like checking if a chef can follow a recipe or just guess the ingredients. But here's the real kicker. These function spaces aren't just abstract math. They're the foundation for understanding why deep networks work. By studying how functions interact in these spaces, researchers can design models that balance complexity and efficiency. It's like giving a sculptor the right tools to create a masterpiece without wasting materials. Now let's zoom out. In machine learning, a big question is, how do models generalize? Recent studies are using tools from dynamical systems to tackle this. For example, the Koopman operator acts like a roadmap for how a model's predictions evolve over time. Meanwhile, researchers are digging into information theory to quantify how much information a neural network needs to learn, like figuring out the minimal instructions for a robot to master a task. To understand this, we need to think about how functions compose. Imagine you're building a system using functions, like puzzle pieces that can be combined in different orders. Mathematicians call this a semigroup, and the way these pieces grow in complexity over time is key to understanding the system's behavior. Now here's the twist. Some systems grow slowly and predictably, while others spiral out of control. Let's start with virtually nilpotent semigroups, the well-behaved systems. Think of them as puzzle pieces that almost commute, meaning the order you put them in doesn't matter too much. Because of this almost commutativity, the number of unique combinations grows polynomially. For example, if you have a few functions, the number of distinct ways to combine them after k steps might look like k2 or k3. Manageable, right? This polynomial growth means the system's complexity increases steadily, like stacking blocks in a tower. But what if the puzzle pieces don't play nice? That's where expanding semigroups come in. These systems are the wild cards. Each function you add amplifies the complexity, like a snowball rolling down a hill. The number of unique combinations now grows exponentially, something like 2k or 3k. This explosive growth is tied to positive topological entropy, a measure of how chaotic a system can get. Think of it as the difference between a gentle breeze and a hurricane. One is predictable, the other is a mess. But how do we even measure this complexity? Let's talk about metric entropy, a way to quantify how many functions you need to approximate a system. Imagine two sets of functions, one that takes you from city A to B, another from B to C. When you compose them like a flight then a train, you get a new set going straight from A to C, but here's the catch. If the second set, the train rides, has a Lipskitz's condition, meaning they don't stretch distances too much, then the whole journey's flexibility is controlled. This leads to a key result. The complexity of the whole trip is just the sum of the plane and train's complexities. Now let's connect this back to machine learning. The tools we've discussed, covering numbers, Rademacher complexity, semigroups, and metric entropy, aren't just theoretical. They're the scaffolding for understanding why deep learning works. By analyzing how functions interact in these spaces, researchers can design models that avoid overfitting, scale efficiently, and generalize better. It's like giving a sculptor the right tools to create a masterpiece without wasting materials. So next time you see a model doing something amazing, remember, it's not just about layers or data. It's about the hidden world of function spaces, where math turns chaos into clarity. Thanks for watching. If you want to explore how this applies to real models, hit subscribe. And drop a comment, what's your favorite magic trick in AI? Until next time.